everybody. Thanks for joining us for the latest episode of the Liu Institute podcast. I'm Sarah Hastings-Simon, and I'm joined today by Ramana, the professor and Simons Chair at the University of British Columbia, and the author of The Power of Promise, a book examining nuclear energy in India. So welcome.
Thank you very much, Sarah. Thank you. I'm happy to be here.
So I'm really excited today to have a chance to talk to you about small modular reactors. We're hearing a lot in the news about the potential for SMRs, and I have a lot of questions that I think many of our listeners would share as well. So maybe just to start out, if you could kind of explain what SMRs are and why there is this interest in them today.
Yeah, so the word SMR, as the name suggests, it involves two particular characteristics, small and modular. So small is, as the name sounds, it produces a small amount of power in comparison with the kind of nuclear power plants that we are used to seeing around right now. So a typical nuclear plant in the US generates about 1 gigawatt, 1,000 megawatts of power. In Canada, it will be around maybe 700 megawatts of power, slightly more. And a small reactor, by definition, is one that generates less than 300 megawatts of power. Right? And it could go down all the way down to maybe 3 or 5 megawatts of power. So it spans a whole range. And then the second term, modular, is used in two different ways. One is to suggest that instead of building one large nuclear plant or any other kind of generation facility, what the utility or the power company that's building these generating facilities is doing is to try and meet the demand in a modular fashion. That is, by adding a little bit of generating capacity at a time. The other sense in which the term modular is used is in the manufacturing sense, that instead of trying to build the whole nuclear plant on the site from scratch, what you do is to manufacture various modules in factories and then just assemble them on site. So that's something which we are familiar with, the way how a lot of today's manufacturing happens, including, for example, the way we see houses being constructed. Quite often there are big pieces that just come from some centralized facility and then are just slapped onto the structure that we see being erected in front of us, which is why houses can get done in a few months sometimes. And so this is a very general manufacturing technique that people have been trying to apply to nuclear power plants. Large plants as well as small plants, right? The only advantage with a small plant is that in some designs, not all designs, you can imagine that the whole plant, or at least some large fraction of the plant, can be manufactured in the factory and transported as it is. This is not possible with a large nuclear plant. But again, I want to stress that the word small modular reactor is only two characteristics, and it says nothing about the specific of the nuclear design. There are a range of fuels, a range of moderators and coolants that are used, and depending on what exact design choices are made, the physical size of these plants can be small or large. There's no connection between that and the generation capacity.
Okay, interesting. So it's not as simple as just one category or one type, but those kind of things come together. And the small is the power, not necessarily the size of the
Absolutely.
plant.
Yeah.
And so why do you think there is this growing interest in SMRs today?
Yeah, so to understand that, we really have to start with the larger picture of the energy sector and the role of nuclear energy there. And it would be fair to say that nuclear power faces huge challenges. So if you look at global electricity generation, the fraction of that is generated by nuclear power has been declining consistently since the mid-1990s. The maximum it ever was 17.5%, and right now it's about 10%. And even in the most optimistic forecast from, for example, the International Atomic Energy Agency, the expectation is that even under the best possible circumstances, nuclear energy can only maintain market share. It's not going to expand, right? What that means is that the fraction of electricity generated is not going to go about 10%. In all likelihood, it will decline to maybe a few percent by the mid-century, okay? All else sort of in a business as usual scenario, that's what would be expected. And the main reason why this is happening is because of the huge cost involved in building new nuclear plants, right? This is something which has been well known, but in the last decade, we have seen a lot of fairly prominent and projects in Europe, in North America, having huge cost overruns and time overruns. So in the United States, for example, in the last 2 decades, 4 nuclear reactors started being constructed, 2 in the state of Georgia and 2 in the state of South Carolina. All right. These were all of this AP1000 reactor design, designed by Westinghouse, which also is a modular construction. Right, the AP1000 is one of its special features is supposedly that it is modularly constructed. So earlier on, Westinghouse used to have a little computer-generated animation on its website, which showed how it could be manufactured in 36 months. Right, various modules will come and get stuck on one on top of the other, and then it'll show within 36 steps that the reactor is constructed. In actual fact, nothing like that happened, right? And the budgets for these, when Westinghouse first was talking about it, was it'll cost around $1,500 to $2,000 per kilowatt. In other words, a 1,000 megawatt plant would cost something like $1.5 to $2 billion. This is sort of what's called overnight construction cost. You have to add financing costs and so on. But in actual fact, when you see the current estimates for the plant that is being built in Georgia, it's in excess of $8,000 per kilowatt. All right, so roughly about 4 to 5 times the initial expectation. All right, and one of those projects, the one in South Carolina, the project was essentially abandoned because of these cost increases and time increases, and in part because of that project, Westinghouse actually had to file for bankruptcy protection. Right, so the chances of building a large nuclear plant at this point are essentially nil. In any of the countries like in the US and Western Europe. And the same thing is true in France, for example, the country which has the highest share of nuclear power in its electricity generation. The Cour des Comptes, the official accounting agency, just came out with a report a couple of weeks ago that suggested that their flagship project in a place called Flamanville has gone from a cost estimate of 3.3 billion euros to something like 19 billion euros. All right. And, the time is also similarly hugely delayed. All right. So none of these countries can really realistically expect to build large nuclear plants. So the nuclear industry's only answer to this is to say, maybe we should build small plants instead of these large plants. Right? And part of this is that when you're talking about $20 billion kind of cost frames, even the largest utilities in the United States, their market capitalizations are a lot of $20 to $40 billion. Right? And so for them to take on a project of this magnitude becomes a huge burden in a way, right? And the financial markets do not react well when a company announces they're going to go on to this kind of a project. So in the only places where they have actually constructed these kind of projects are those states where there is a public utilities commissioner who says, okay, we think that this project is justified, therefore the customers, the ratepayers will be paying for the cost of this, right? And that's not something which is justifiable anymore. So small reactors are seen as easier because hopefully the overall cost will be lower. But there are problems with that, and I'll get to that later.
Okay. So kind of looking forward then with the idea of SMRs, is this a new idea? Like, are there SMRs operating that, could inform how things are built today? I do note that in the discussion, it's usually talked about as a new technology, but obviously nuclear is not new. So what does that history look like?
Exactly. That's a great question. So the answer is yes and no, right? So any reactor that is built today is going to be new technology by definition almost, right? A motor car that is built today is not the same as your motor car that's built in the 1960s. So everything in that sense is new. At the same time, the general idea of making small reactors is not at all new. In fact, all reactors started by being small, right? The first reactors that were built in Canada, in the US, in India, everywhere were small reactors. There were a few hundred megawatts at most. And even at that time when all these reactors were being discussed in the 1950s and 60s, it was very clear to planners that they would also have to develop small designs if they wanted to meet markets which require relatively small amounts of power. whether it is in developing countries, whether it's in the rural areas, all the kind of rural cooperative electricity suppliers would not be able to afford a large nuclear plant. That is obvious to them, right? So there was always a push for that. So there were a few which were built in the United States, especially. The Atomic Energy Commission had a program to support the construction of small reactors, and there were about 4 which were built around the place, and all of them were shut down well before they actually completed their lifetime, mainly because they tended to be too expensive, the power that they generated, all right? And likewise in other countries. So in India, for example, for a long period of time, India built pressurized heavy water reactors, which were based on a design they got from Canada in the late 1960s. And that used to generate 220 megawatts. And the Indians persisted with that design and sort of minor modifications of that till the 1990s. Then they also decided the way to go forward is to actually scale up the size. So the current heavy water reactors they're building are all designed to generate 700 megawatts.
Okay, so there is a longer history. And when we hear this discussion about SMRs today, it definitely has an element of technology development and new technologies. I was wondering if you could talk a little bit more about what the challenges are around development of new SMRs and commercialization. Is this something that is theoretically possible and it's an engineering challenge, or what are the types of barriers that we're facing in getting to really building and deploying these units?
Great question again. There are sort of 2 ways in which to think about challenges, all right? There are challenges to the developers of the technology, and there are challenges to public policymakers. And the 2 are not the same, all right? We should not identify the interests of developers with the interests of public policy. Just want to sort of put that out in front. Let me first talk about what the challenges, and I'll explain why they're going to be different. So the main challenge is that there's a reason why the nuclear industry moved from small reactors to large reactors. And this is because always nuclear power had a problem of economic competitiveness. It was always more expensive simply because of the fact that a nuclear power plant is basically a very complicated way to boil water. That's what it is, right? And what you're trying to do is to use a very inherently dangerous process of fission to do this boiling of the water. So you have to put in a large number of safeguards to make sure that there is no accident. I'll come back to that later. But because of that reason, nuclear power is inherently an expensive way of doing it. And the only way that the nuclear industry initially thought they could deal with this problem is to scale up the size of the generation plants, right? And use what's called economies of scale. So the idea is that if you're having a nuclear power plant that is generating 3 times as much power, then it would get 3 times as much revenue, but it will not require 3 times as much concrete or 3 times as many operators in the plant. And so you can cut down on the cost and raise the revenue. That's the idea, right? And it does work to some extent, but what we are finding now is that by the time you get to the 1,000 megawatts, 1,500 megawatts range, that doesn't seem to be working out so well, right? For various reasons which have to do with the complexity of the design. Okay, so that's so when you go back to smaller reactors, you're losing out on those economies of scale, right? So what you're going to be doing is that even though the overall nuclear plant is going to cost less compared to a large plant, it'll be generating far less energy, right? And so the dollar per kilowatt value, the cost per unit of generation capacity goes up significantly, right? And this is sort of well understood in the power sector and usually is characterized by a power law, which is sort of going by a 0.6 power or something of that sort. So if you think about that kind of a cost, then what happens is the generation cost of electricity becomes even higher, and nuclear power already has an economic competitiveness problem. So this is going to become worse with small reactors. The answer that the nuclear industry gives to this is say, yeah, we know this problem. There are 2 ways they can try to deal with it. One is to say, oh, this is new technology, so you cannot scale from the old kind of technology. And I think that's a very dubious thing because there are some inherently common properties, which all of them have. The second is that they'll say, okay, we can compensate for the loss of economies of scale by doing this manufacturing in factories. That's why they stress the modular term, right? And so you can save on that by building these large factories and manufacturing all the components there and just doing the assembly on site. And that's going to somehow reduce cost through the economies of both mass manufacture as well as learning of different kinds. And the problem here is that there are two sets of problems. First, the history of learning in nuclear power has been the other way around. In other words, the costs of nuclear plants have increased over time rather than decreased. And the simplest way to think about it is that as you have more experience with nuclear plants, you realize there are more ways of having accidents, right? More vulnerabilities. So Fukushima, for example, taught us that the backup power sources should be, there should be multiple ways of sort of supplying backup power, et cetera, et cetera. And so you have to try to plan for those kinds of accidents that will increase the cost of the plant, right? So this kind of cost increase is something which we see everywhere, especially in the two largest markets, the United States and France, right? Both of them historically costs have gone up and it's been very well documented. The second issue is that even if you were to assume that, okay, this is a thing in the past, from the future, at least we can save through mass manufacture and learning. If you assume some kind of a learning rate, which is reasonable, like let's say 5%, then the number of plants that would have to be built in order to compensate for the loss of economies of scale is huge. Hundreds to thousands and even tens of thousands, depending on what you assume to be the learning rate, what you assume to be the savings, the loss of economies of scale, et cetera, et cetera. These are all parameters which we really don't know because we don't have large-scale experience with many, many nuclear plants. So you have to make approximations. But in any case, it's very clear that the numbers that will be required will be too high, right? And the question is whether there is a market that is willing to build all those expensive lead-on plants. And that's the third problem, which is that you have a chicken and egg issue here, right? In order to make cheap nuclear plants, you have to manufacture huge numbers of them. But in order to set up the factory to manufacture them, you have to be assured that there's going to be a large enough market to set up that factory in the first place. You're not going to set up a factory in order to manufacture one plant, right? Just as you're not going to do that for making one car, right? So it's the same kind of idea. And this is a huge challenge for the purpose of developers, right? When you come to the public policy people, and so what the developers basically say is, look, the governments need to sort of pay for all the loss leaders, essentially. You have to subsidize that. But what the public policy maker should be asking is, how many of these plants can I subsidize? Realistically, right? If you're talking about hundreds of plants, each costing a few $1 billion, that's a huge amount of money to be subsidizing, right? For very uncertain gains. So that's, I think, the essential thing. And to think about, also to put a context to this, there is a nuclear plant that is being, SMR, that is being pushed for deployment in the United States by a company called NuScale. And NuScale so far has spent roughly $1 billion between that and the amount the US Department of Energy has given it as grants. And the expectation is it will require at least another $500 million before even the Nuclear Regulatory Commission in the US can actually certify this as being ready for construction, as safe enough for construction, right? So you're talking about $1.5 billion upfront before you even start building the first plant, right? So is the private industry actually going to be willing to pay that kind of money is a question.
The next question that I had for you, I think you've sort of answered it already through what you said, but I think it might still be interesting to revisit it and kind of compare and contrast, which is how do those challenges, say around, starting from a perspective of high cost, for example, compare with other technologies that have successfully come down the cost curve, right? Because someone might have made some similar arguments, say, about wind or solar a few decades ago, saying that, they're very expensive. Obviously, maybe we're talking about different scales and things like that. But I was wondering if you could just kind of draw out the differences between those two industries, because I think that's quite relevant.
Yeah, I think it's a great question and something that comes up a lot, which is the question of why can't we reproduce the learning processes that happened in wind and solar in the nuclear field? And to some extent, yes, it is possible. You can learn a little bit from them, but there are inherent limitations, right? To start with, I think the technologies are fundamentally different for the reason I mentioned earlier, because there is no way that nuclear power can become less complicated in some ways than it already is, right? Because of the need to be containing all the radioactive materials that are being produced, to be considering all the accident scenarios. And accidents in the nuclear field are unique in a way that is not the case for solar and wind. I mean, if the solar panel falls down, somebody might get hurt if you're standing underneath that, and so on and so forth. But really doesn't compare with the kind of long-lasting radioactive contamination that we see around Chernobyl, for example, where 35 years after the accident, we still have large tracts of land which are uninhabitable today, right? So this is sort of unique in the sense of the scale, spatial scale, as well as the temporal scale of the potential thing. Even though it's a low probability event, you have to plan for the possibility, right? And so that's why I think a huge difference, right? The second is the amount of time it takes to construct one of these things, right? So in the case of a wind turbine or a solar plant, typically you're talking about 6 months, 1 year, 2 years at most. Whereas here, the average time scales of roughly the order of 10 years, right? That's the time frame it takes to construct one of these large reactors, right? And maybe a small reactor might be a little bit less, but maybe 5 years, right? But even there's a huge period of time which you have to spend to get the permits, to most importantly, raise the billions of dollars that you have to sort of use to spend to construct the plant. And that whole process takes a lot of time. So for you to keep repeating experiments, you're talking about decadal time scale. So even if you can do the learning, it'll take you 50, 100 years before you can kind of get to the speeds of learning that you see in the other industries.
Yeah, that's really interesting. And I think that time scale is obviously with all the constraints that we're facing around energy is really important. There's one example that I've always wondered a little bit about. We've had these nuclear submarines roaming around the seas since, I guess, World War II times. Are those powered by something that is an SMR? Why can't we just park one of those on land and declare victory in creating SMRs?
Right. Great question. So SMRs don't have the problem of trying to give an existence proof, right? As I mentioned, we have had small reactors way back in the 1950s and 60s. So you can absolutely park one of those things and try to generate electricity. But submarines are fundamentally different. The constraints that a nuclear reactor and a submarine have to deal with are quite different from a power plant that is generating electricity in a potentially competitive electricity marketplace, right? So first thing is that in the case of nuclear submarines, what their main attraction is that they can travel for a long period of time underwater without refueling, right? This is something which no other fuel can offer, right? And it's something which is very desirable for people who want to drop bombs on faraway places. All right, I'm not one of them, but that's a different issue, right? So, but those people don't seem to care about how much it costs to develop one of these things, right? So they operate under essentially no cost constraints. In the electricity market, on the other hand, there's a number of ways by which you can generate electricity, and many of them are far cheaper. So then why would you want to plonk one of these things? The second is there are places where this is being done. So Russia just has one of these KLT-40S that they started operating out in sort of Siberia somewhere, and it basically goes on a barge. But you're paying for a huge amount of infrastructure, and it's just not going to be economically viable.
Yeah, so can you say a little bit more about the specific niche applications? Like, might there be some use cases that are remote or in some other way, other than just the submarines, where SMRs make sense? Is there a potential for that?
Yeah, so there's been a long-standing idea that, especially in Canada, that there are all these remote regions, the remote mines, indigenous communities, and so on, which are off-grid, which are now being served with expensive electricity from diesel generators, right? And so the question is, can a nuclear plant make sense? So my colleagues here and I actually just published a paper in Energy Policy where we looked at this topic. There are two problems there. The first is that there's the chicken and egg problem that I mentioned earlier. If you sort of sum up all the total demand from all these remote areas, it does not amount to be enough to be considering construction of a factory, all right? And this is assuming that every possible place that has the potential electricity demand goes ahead and builds one of these, right? And there are huge problems with that, and I'll come to that in 1 second. But even in the most optimistic circumstances, you're talking about a few hundred megawatts of demand. All right. And that's really not enough to construct a factory. The second is we also looked at the cost of doing one of these things, right? So what you'll have to do is to go really down the scale of generation. You have to talk about 1 megawatt, 2 megawatt, 3 megawatt kind of designs, right? Because most of these don't have enough demand to be able to even operate a 25 megawatt reactor. All right. So then at that point, you're really losing out a huge amount on economies of scale. And what we found was that the cost of generating electricity could be an order of magnitude more than even diesel. All right. And so really, even if you can sort of say, look, you guys are making unrealistic assumptions or really difficult assumptions, we have this great technology, they would have to come down by something like 90-95% in cost compared to what is expected before it even breaks even. All right. And already what many of these communities are doing is to say, we will not be able to completely maybe get over diesel at this point, but we can definitely lower the amount of diesel we are using by adding wind, by adding solar, by adding hydro in those places where there is some limited hydro and so on. And lastly, we also have a time problem. And the time problem is that by the time these SMRs actually are developed and deployed, it could take up to a decade or more, right, before they are even ready to be deployed. During that period, we also have to consider the other technology that's been falling rapidly in cost, which is batteries, right? So if a form of storage becomes economical, and it looks very likely that by 2025, 2030, we might be able to meet that point where a standalone system based on renewables and batteries might compete with these very expensive forms of nuclear power generation. Right. And so really, is somebody going to be willing to bet saying that is not going to happen and nuclear is going to be the only option possible?
Mm-hmm. Right. Well, maybe I'll wrap up by asking you to look into your crystal ball a little bit and tell us what you think the debate and development and, that project that you mentioned in the States, how that might play out over the, coming decade, what we might see.
Yeah, I think over the next decade, we might see some prototype SMRs that may be constructed. And this is a slim possibility, given that even this new scale project that I've been talking about, they've been trying to sell it to a group of municipal power suppliers called UAMPS, Utah Association of Municipal Power Suppliers. And they have not managed to find municipalities that are willing to actually subscribe, buy into the project, right? More than 120, 150 megawatts at this point out of the roughly 720 megawatts that the power plant will generate. All right. So it is possible that because the US Department of Energy is backing it so much, the nuclear industry is backing it so much, maybe one or two prototypes might be built. But I cannot imagine that it's going to solve all the problems that nuclear power faces. And so people who are seeing that project actually being deployed will say, oh, this is not going to work for us. So, I don't imagine there'll be a huge market that's going to come. And this is because I think the other thing to remember is that nuclear power plants, other than this, I'm mostly focused on economics, kind of mentioned the problem of safety. There are other problems also which confront nuclear power. There's the problem of the radioactive waste that it generates, which there is no effective solution so far, no demonstrated solution so far. And in the case of SMRs, for the same kinds of reasons why the cost goes up, the smaller size means that there'll actually be more waste generated per unit of electricity generated, simply because the efficiencies will be lower there. And then likewise, the proliferation impacts, the amount of enriched fuel it will require, the amount of plutonium it will generate per unit of electricity generated will also be greater. All right. And so for a number of reasons, it will actually compound other problems, which it makes it difficult to imagine a very large scale expansion of SMRs. And so I don't see them as a solution to the challenges that nuclear power faces today.
Great. Well, thank you so much for joining me today. It's been really interesting. I've learned a ton and really enjoyed it. So I appreciate it and look forward to seeing more of your work looking at some of these challenges going forward.
Thank you very much, Sarah. It was a real pleasure, and thank you for the great questions.